Hello, Algebra students. Today we are going to be learning about geometric sequences. A geometric sequence is an ordered list of numbers in which the ratio between each set of consecutive terms is the same. That means that each term is multiplying. So the common ratio is the ratio between each pair of terms that are next to each other in the geometric sequence. Notice in this example, each term multiplies by 5 to get to the next term. That is a geometric sequence. The common ratio would be 5. So in the first example, we're going to tell the difference between a geometric or an arithmetic sequence. If you remember back to our 4.6 notes, an arithmetic sequence adds to get to the next term. So we're going to determine if these examples are adding to get to the next term or if they have a common ratio and are multiplying like a geometric sequence. If it's neither, then it's neither. All right, so in example A, we have 120 and then 60 and then 30 and then 15. Each term is dividing by 2, which means it's also multiplying by 1/2. 120 times 1/2 is 60. 60 times 1/2 is 30, and so on. That means my common ratio is 1/2, and it is geometric. All right, in the second example, I have 2, 6, 11, 17. They are not multiplying, so I'm going to find the difference between each term. From 2 to 6, it adds 4. 6 to 11, it adds 5. 11 to 17, it adds 6. It's not adding the same number, so it can't be arithmetic. It's not multiplying, there's no common ratio, so it can't be geometric. Therefore, B is neither. All right, and lastly, we have 5, 1, -3, and -7. These do not seem to have a common ratio, so let's find the difference. 5 to 1, it subtracts 4. 1 to -3, it subtracts 4. -3 to -7, it also subtracts 4. So it looks like the common difference is -4 or -4, and C would be arithmetic. Zoom out so you can see all of our examples before we move on. All right, so just like we did with arithmetic sequences, we are going to write the next 3 terms of this geometric sequence. Before we write the next 3 terms, we need to figure out what the common ratio is. So to get from 64 to 16, it divides by -4, or we could say it multiplies by -1/4. All right, so 64 times -1/4 is -16. -16 times -1/4 is 4. 4 times -1/4 is -1. So if we continue, -1 times -1/4 is going to be +1/4. And then if we do 1/4 times -1/4, it's going to be -1/16. And lastly, -1/16 times -1/4 is going to be +1/64. So we have 1 term, 2 terms, 3 terms. Those are our next 3 terms. All right, next we are going to graph this geometric sequence. Now remember, a sequence is an ordered list of numbers. So my first term is 64. I'm going to treat the terms as the y values, and then we're going to say x is the order the term is. So 64 will be paired with 1. We'll plot that as 1/64. 32 is our second term, so we'll plot that as 2/32. 16 is our third term, so we'll plot that as 3/16, and so on. Pause the video for a second to get your points plotted, and then play it back and my points will appear. All right, so now that you have your points plotted, I would like you to think about what you notice between these points. Now in chapter 6, we've been dealing with exponential functions that have had the exponential curve. If you look at the terms of a geometric sequence, you connect the dots, they also have an exponential curve. So what you should notice is that these are exponential. All right, take a minute to graph this geometric sequence. See if you notice the same thing. All right, and once you have these points plotted, you'll notice that it is an exponential growth function. If we connected the dots, it would have an exponential curve increasing. All right, so lastly, we are going to write an equation for a geometric sequence. So I'd like you to think of an as though it's y, and then n as though it's x. So if you remember our exponential functions, we had y equals ab to the power of x. So something times a base with x as the exponent. Now a geometric sequence is super similar, and a sub n, remember that means the nth term. So the nth term is decided by the first term. So here a sub 1 is the first term, times r is going to be our common ratio. And then n is like x, it is the actual term. Notice it's n minus 1 because in our original exponential function, it was based on the y-intercept. So because we start with x as 1, the first term, the y-intercept would be the 0th term, kind of like we did back with arithmetic sequences. Anyway, it has to be n minus 1. So the term you're looking for, minus 1, is the exponent. All right, let's practice writing some of these. Okay, so if you'll remember from the last slide, we had a sub n, or the nth term, equals the first term times the ratio to the power of n minus 1. So we have 3 pieces of information we're looking for. First, I need to know the first term. In example A, the first term is 2. Also, I need to know the common ratio. If you're looking 2, 12, 72, 432, each term is multiplying by 6. So I'm going to set up my function. I would have a sub n equals the first term times the ratio to the power of n minus 1. And then to actually find that nth term, I need to know what term I'm looking for. So notice it tells us in the example a sub 10 means the 10th term. I'm looking for the 10th term. So we're going to write a sub 10 equals 2 times 6 to the power of 10 minus 1. Now we can plug this into our calculators, and the 10th term is a huge number. We have 201,55392. That is 20,155,392. All right, pause the video, see if you can do example B on your own, finding the pieces of information that we went over in example A, and then play it back to see if you got it right. All right, so we have our first term is 432. We have our common ratio. This time it's getting smaller, so it's a fraction, 1/6. We're dividing by 6. So we set up a sub n equals 432 times 1/6 to the power of n minus 1. You might have put parentheses around that. That's awesome. Then we plug in a sub 10 equals 432 times 1/6 to the power of 10 minus 1. Type that into our calculators. We get the 10th term, 0.0000. That's 4 zeros after the decimal. 4286694, so we're just going to round to 7. All right, last example. Clicking the zoom out button on a mapping website doubles the side length of the square map. After how many clicks on the zoom out button is the side length of the map 640 miles? All right, so we're writing an equation. Remember, our geometric sequence is the nth term equals the first term times the common ratio to the power of n minus 1. A couple of pieces of information I can get from this table. The first term is 5. And it looks like the common ratio is 2. 5 times 2 is 10. 10 times 2 is 20. It also tells us in the problem that it doubles the side length. So the zoom out clicks is like our n, or x, the term that we are on. And we want to know how many clicks, so the n value, if the side length is 640. So 640 equals the first term times the common ratio to the power of n minus 1. Now we have to solve this backwards. So if we're thinking of GEMDAs backwards, exponents come after multiplication when we're doing it backwards. So first we're going to divide by 5. 640 divided by 5 is 128. So now I have 128 equals 2 to the power of n minus 1. Now I know that 2 to the power of 7 equals 128. So we can figure that out by doing 2 times 2 would be 2 squared, which is 4. Times 2 is 8, so that's cubed. Times 2 is 16, so that's the power of 4. And then keep going until you get to 128. So if I know 2 to the power of 7 is 128, that means n minus 1 has to equal 7. So n is 8. Our answer would be 8 clicks. All right, guys, that concludes our geometric sequence notes. So if we are thinking of our summary questions, how are geometric sequences different than arithmetic sequences? Well, geometric sequences multiply to get to the next term, where arithmetic sequences add or subtract. When you graph a geometric sequence, the shape is an exponential curve. The equation we just went over, you need to know the common ratio and the first term to set up an equation for the nth term. And how you use the equation in a real-world problem? Well, look back at the example we just did. All right, guys, your homework today is going to be page 336, 9 through 27 odd. You do not have to graph 19, 21, or 23. So you are just finding the next terms in an arithmetic sequence, finding the common ratio, and writing a function. We will go over solutions tomorrow when I return and review for the test on Friday.